Hello dears. And this week we will study design control system using the root locus method. So root locus actually is a certain mechanism, or it's a graphical way to show us the flow of poles or the movement of poles over S-plane as the gain of the transfer function change. So we will see this after a while in the example coming on the next slide. It shows us how the change of pole will affect the change of the gain will affect the pole location on S-plane. If we consider this system with open loop transfer function as K1 multiplied into K2 over S into S plus 10, if I want to draw or show the root locus of this system, we will find its closed loop transfer function, where the closed loop transfer function found to be K over S squared plus 10S plus K. So K will appear in the denominator, where K is the product of K1 and K2. So K1 and K2 is equal to K. So now let us check in the next slide if the value of K starts from certain point and we increase it until certain value, how the poles are going to change their position. So here is the changes. We are going to assume that the gain equal to 0, pole location will be as you see here. So if the gain changed to 5, the pole location will be at this point, and so on. If the gain is 10, the pole location will be here and here. If the pole location, the gain is 15, for example, 15, the pole location will be at -8 and -2, and so on. So we are going to reach to a point where with certain gain, which actually 25 is shown here, the two poles going to come at the same location. And after that, if you increase the gain more, you will find the pole are going to go toward complex quantity. I mean, it will have real and imaginary. So this root, the movement of the poles are going to be represented with what is known as root locus. So we are going to find that it's going to take this way and this way. This is actually known as root locus. Let us get idea about this movement. It's described in the next slide. So the changes of the gain will change the position of the poles, which will result in something we have studied in the transient response. Like for example, starting from 0 up to 25, when the gain equal to 0 up to 25, the pole were on the real axis. It was here and here, then here and here, then here and here, and so on. So as it's moving during this time, you are going to get the system response is overdamped. Okay, until we reach to the gain of 25. When the gain equal to 25, we are going to get the two poles in the same location, and this is called the critical damp. How about if we are going to more than 25, I mean 25 to 50, or even more than 25? More than 25, this is when the two poles in the same location. So we said the poles are going to move in the complex location. So it will keep flowing till infinity and till infinity as the gain is changing. So from here we are going to realize, or we will figure out the transient response from the root locus. Means the pole is going to tell me about some behavior or some transient response parameter, as we have discussed in the transient response. Also, if the gain is go to more than 25, this is going to affect zeta, affect omega n. Let me put example here. If let us say this is the pole location, if the pole location is this point, or maybe the pole location will come here, or maybe the pole location will come here. What is the difference between one and the other? At the first position, when it's here, the angle is this much. The angle theta is this much. We know that cosine of theta is equal to zeta. And if I increase it to this much, the angle will increase. That means cosine theta will be different, which means zeta will change. Same thing with the third position. So with every position, the angle is changing. That means zeta is changing. And also, if you notice, in each case, omega n will change, omega n will change, and omega n will change, which means with each position, we are going to get zeta and omega n change. And if you remember, when we studied the transient, we said with the availability of zeta and omega n, we will be able to calculate any of the time response parameter. And it's going to change as those parameters change. Means if zeta and omega n change, those times are going to change. That's how we can get some idea from the root locus on how the system will behave as the gain change. Now, to sketch the root locus, we are not going to follow the style mentioned in the previous example. I mean, I'm not going to find the location of pole one by one. What am I going to do? We are going to follow certain rules, and by the end of applying those rules, we will find the root locus ready. What are those rules? He's saying here the number of branches. So the number of branches in the root locus is equal to the number of poles. Just keep it in your mind, and after a while you will catch it. Number of branches equal to the number of poles. And symmetry, the root locus usually symmetrical about real axis. So if this is the real axis, whatever found, let's say I will find that there is a curve here of root locus at this location. That means for sure you are going to find the same curve here. If I find that the root locus going this way, that means from the other side it will go to the other way. So it's going to be symmetrical about real axis. Okay, in this rule called real axis segment, in this rule he will tell us about the segment drawn on the real axis, how it's going to be placed, how we can put it based on what idea or rule. He's saying here the root locus to the left of odd number of real axis element. Real axis element here, or real axis poles or zeros anyway. I'm saying element because it's either pole or zero is the same. This is one of the element, this pole, and this pole is one of the element. This zero is element, this zero is element. So after odd number of element, you are going to find there is a line. How can I describe it in different way? I would say here, if you have one element, after one element there will be a line. If there are two elements, no line. If three elements, there will be a line. This red color is root locus. So if you notice behind the root locus, there will be odd number of elements. Behind this one, there is one. Behind this one, there are three, and so on. That's what he means by real axis segment. Starting and ending point. So where the root locus will start and where will it end? Here he described it. If we have a pole distribution as pole and zero, we have pole at -1, pole at -2, 0 at -3, and 0 at -4. How am I going to draw the root locus here? First of all, I will start with whatever rules I have studied so far. So we are going to put the real axis segment. So from the real axis segment, I will find that there is line here and line here. Now, the starting and ending point, which this rule, it's saying every pole will start from its location and it will move until zero. So pole is going to meet a zero at the end. At the end, the pole will meet a zero. That means if there are two poles, as you see, two poles and two zeros, finally they are going to meet. So we will find that a pole will start at certain point, like this point. Let me change the color. This point, and it will go this way, this way, this way, this way, and it's going to go back to this zero. Similarly for the other one, if I consider the other one, the pole will start here and will continue its way to zero. Somebody will say, based on what you are going to take this route, we are making it based on other rules we are going to study later, and in the same time I have to keep the symmetry. So notice here, we get the real axis segment, we get two branches here which equal to the number of poles. We have the starting point and ending point is clear. starting point is pole, then we are going to go toward 0. We will go toward 0. And here, starting from the pole, and we will go toward other 0. That's the idea. Concept of infinite pole and zeros. Now, what will happen if the number of poles and zeros and on S-plan are not the same? If the number of poles and zeros on S-plan are not the same, we are going to assume somehow that there is, the difference between the number of poles and zeros are going to be exist in infinity. What is the meaning of this? Let us consider this example. In this example, we are having a system with 3 poles, one at 0, one at -1, one at -2. These are 3 poles. Where are their zeros? We don't have any 0. If you notice, no zeros available. That means for this system, there are 3 zeros available at infinity. They are available at infinity. And you will see after a while how to draw them. Now, if I want to start taking the line toward infinity, let's consider the 3 elements mentioned in earlier. Let's say -1, -2, -3. Let us start drawing the root locus. To start, you'll find there is one line here and one line here. Now, it's very clear that this pole is supposed to go to 0, and this pole is supposed to go to 0. I mean, this one to 0, this one to 0. There are no zeros on S-plan. So where are the zeros? They are at infinity. And from the direction of flow, we know that this pole going to this direction and this pole going to this direction. So at certain point, they will they will meet, and then they will go toward infinity. But where to go? I mean, in what line they are going to take toward infinity? Are they going to go straight up or straight down or this direction or this direction? So what are the direction these poles going to take toward infinity? That's what we know as the behavior at infinity. In the behavior at infinity, we are going to find the way for these 2 lines to go to infinity. Let us redraw them. So we are having, this is S-plan. We have 1, 2, and 3. We agreed that there is root locus here and root locus here. So I need to know for these poles what direction they are going to go toward infinity. Direction means angle. So I need to take these 2 with certain angle toward infinity. What is that angle? We will calculate the angle. The angle is to be calculated from this equation. I will explain it after a while. But before I explain the angle, I need to know where to draw the angle. If I say the angle is 60, for example, where to put the 60? Should I put the 60 at this point or at this point or this point? So 60 is to be drawn at certain location called sigma. So we are going to get the point sigma where we will draw the angle toward infinity. So sigma is equal to the finite poles minus the finite zero. Means the poles exist in the S-plan minus the summation of finite zeros exist on the S-plan divided by the number of finite pole minus the number of finite zero. Let us say we calculate them and we found that the point is here. This is sigma. So if this is sigma, we will calculate theta. Theta, number of angles to be calculated is equal to the number of poles or zeros toward infinity. So if you notice here, we have 1, 2, 3 poles to infinity. That means I need to generate 3 angles. I will start with theta 0, theta 1, theta 2. Why I am calling them by this way? Because I will calculate theta 0 as 2 into 0. K will be equal to 0. 2 into 0 plus 1 into pi divided by the number of poles minus the number of zeros. Okay, number means number, 3 poles, 4 poles, 5 poles, something like this. When I want to calculate for theta 1, K will be equal to 1. When I calculate for theta 2, K equal to 2. And we will calculate. You will find after a while by calculation that whenever I have 3 poles, you will find that the 3 angles, one of them will be 60 degrees, the other will be minus 60, and the third will be 180, which means the poles are going to start at certain point. We will calculate it later, and they are going to meet with this 60 toward infinity, meet with the 60 toward infinity, and the 180 will be for this pole going toward infinity. We will see this after a while.